Hi, so here's where we were at the end of the last ALU build video. I did the tidying up on the circuit, but we've got the ALU inputs coming over onto this board here, controlled by these four control lines. So I can select from the GPRs into either the left or the right hand input. So now it's time to start actually building some ALU logic. I'm not sure quite how far we're going to get in this video, but I'm very keen to actually get some computation done. But I think initially these control lines, I'm just going to move them away because they're just going to get in the way for the time being. So let's look back at the ALU design. So we've got a number of different components here which we'll try and break down the build into, and we need to work out a good place to start. Now we're really only computing once we get some data in and take it all the way to the output. So I think it's going to be best if we focus on trying to achieve that as soon as possible. So for initial build, let's get rid of shift and bitwise logic. Let's not worry about the carry or the flags. Okay, so these latch chips are kind of essential for timing what's going on, and add is a nice, clean, simple thing to implement first. So let's try and do that. Okay, so I want to get this is the 574 D-type latch chips that we've used for storage in a lot of places. Alright, I'm just positioning these so we can line them up with the obvious place for these LEDs, but I'm going to turn this LED array around so we can use the outputs directly into here for the time being. Okay, this latch chip also has an output enable on pin 1 here, and it has a load line. Okay, for the time being, I think we should hook that into the clock. Now we can bring the data straight off the top of this wire and into the inputs of the latch. Okay, so these pink lines are basically a stand-in for the shift unit, and we're going to need a second latch. Okay, it's going to be a bit more difficult to bring the wires all the way up here for the right-hand side input. I'm going to shortcut it with a DuPont cable. These connections are only temporary after all. Okay, I doubt we're going to get as far as putting the values back onto the bus from the addition, so I'm going to stick some result LEDs in. I think it's probably a good idea to have those anyway. Okay, so now we're going to need to perform some addition. Now in the 74LS series there's actually only a couple of addition chips, and this one has the word fast in it, so seemed like a good place to start. So what this is a 4-bit binary adder with fast carry. So power and ground where we'd expect them to be, and then we've got 4 A inputs, 4 B inputs, and 4 outputs, and then we've got C0 and C4. So what we've got is a carry in and a carry out, I believe. So let's have a look at dropping some of those chips in. The numbering on these is almost imperceptible to me, so hopefully they are 74LS283s, or this might be quite a short video. Okay, so these are 4-bit adders, so I've added 2 of them, which we're going to need to add the full 8 bits. And let's start thinking about how we're going to wire this up. So we've got a carry in line. Now for the time being we don't want to do anything with that, so I'm just going to tie that down. Carry out, I don't think we need to worry about immediately, but the carry out from this first chip, this is going to be adding together 2 numbers which are 4 bits, so that's 0 to 15, and if we add those together we can't store the result in 4 bits, so we have a carry output. So that goes to the carry in of the next one, and that way we can chain as many of these together as we want. So for 4-bit numbers we only need 1, for 8-bit we need 2, 3 would give us 12-bit numbers, and 4 of them would give us 16-bit numbers. So we'd need 8 of these to do a 32-bit add, or we can use some clever programming to pass numbers through it multiple times and hopefully add larger quantities. Now if we go briefly back to the pinout, we see here we've got A1, B1 and the output 1 here, and A2, B2, and A2 and B2 are swapped over from 1, and on the flip side it's A then B then B then A over here. So this is really quite complicated. I think it's going to be difficult to keep the wiring neat, but let's do the best we can. Okay, so what I'm doing first is wiring up the outputs into the LEDs. I presume the input lines are all going high naturally. It'll be easiest to get at bit 4 next, I think. And bit 3. Sit on top of that. And while we're here, I'm going to connect the carry output from this lower order chip to the carry in of the next one up. So that is... Okay, we've managed to keep that fairly neat, but I don't know how long that's going to hold for. Okay, this is about as far as I got with my careful planning on the wires. I think it's going to be easier if we create a bit more space over here. Let's leave that to one side for now. Actually, I'm going to leave connecting those up. Okay, so we need to connect the left hand side least significant to A1, which is there. Actually, it could be better to do all the B's first. Let's do that. Okay, so B1 is there. Okay, so that's the lower 4 bits of B done. So this needs to go to A1 on this chip, which is that one there. try and bring it over the top. No, that's the wrong one. Okay, I need to check these ones now because I just happily started plugging these ones in the wrong wires. So that is B2. Third pin across, B4. Yeah, that's good. Okay, so I think that's all of the right-hand side inputs connected to the 8B inputs on the two adder chips. Now I need to do this side. We've just got these last 8 wires from the left-hand side input to wire into these 74283 adder chips. I've got an idea actually. If I put one of these resistor arrays in here, it should pull all of the right hand side down. Then in theory I think we should gradually expose this input if we're getting these wires correct. So the input to the right hand side is now 0. So yeah, so what we've got here should start appearing here. And we've connected the second bit, bit 1, in, and yes, that's low. Okay, I'm going to skip the next 2 bits because they come out of the top side of this chip, or sorry, go into the top side of this chip. I'd like to finish off all the ones at the bottom first. I joked earlier about liking these particular adder chips because they got the word fast in. But the exact terminology is actually with fast carry. And that's kind of interesting. So if you think about each of these, you've got 3 separate inputs. 2 4-bit inputs, which are 0 to 15 each, and the carry input, which is 0 or 1. and effectively it produces a 5-bit result, which is the addition of those 3 values. But you can break down the internals of one of these and think in terms of a single bit of addition, where you've got a carry bit coming in, the A and B inputs coming in, a result and a carry out. And you could have 4 of those in a row and wire them up through this. But if you look over here, there is actually a logic diagram for it, and it's not wired up like that. What you've actually got is a more complicated set of carry logic where the outputs are each successively dependent on more of the inputs. So if you look at this first one, it can resolve that with just a couple of inputs. But the main combiner is these NOR gates here. And this one's 2 input, this is 3, this is 4, and this is 5 inputs. So it's basically taking the carry controls from each of these to compute the result. So if you count the maximum number of gates between the input and each of the outputs, I believe it's 3 in this design. So the carry out is produced at the same time as the outputs of the other lines. Whereas if you did this with the classic single bit carry, then what you end up with is this first output bit is quite a short path from the 2 inputs and the carry in. But all the way up to the end here for the carry out, you have a kind of a cascading effect where you could end up lining half the logic gates in the circuit in a row, and you end up with quite a lot of latency before that final carry bit resolves. Difficult to know what the right path for some of these is. I think it might be better to do the penultimate bit there. It has to go down to pin 15 there, next to the power line. I'm watching these lights out of the corner of my eyes, trying to work out if it's doing the right thing or not. It's not the easiest thing to tell. It should be a lot clearer once we get the last few lines in. Okay, well, it's definitely not doing the right thing at the moment. We seem to have a couple of bits that are wrong. Okay, so the 3rd bit is on. So there's 3 possibilities here. We've got the 3rd bit on left is high, the 3rd bit on right is high, both of the 2nd bits are high. So the 3rd bits are here, B3, A3 is this one, which has nothing plugged into it. That's the correct one at this point. Okay, need to recut that wire. It was inevitable that I'd make a mistake or two on these. The bends are all too complicated. It doesn't feel terribly neat either. It's, oh, the 7th bit is wrong. So once again, there's 3 possible errors here, but let's assume that it's the simplest one, which would be either this line. Where's that going? Neither of those look right. Yeah, I'm a total idiot. That other wire was correct the first time. Got the same problem. This wire goes 1 pin to the left of where it should be. Okay, that is at least producing the right result at the moment. Let's have a play and see if we can understand what's going on. So if I set the carry bit, then this is interesting. So this number is just running through the powers of 2 to make it bounce backwards and forwards. It's the input we've got here. When that is 1, so we're adding 1 to it. So when that gets down to there, the result is 2. So just this LED comes on during the bounce. So that's working correctly. Okay, is there any way to better test this? So here's a problem. If we put this in here, yes, so these numbers don't slide up and down in lockstep. One moves before the other. So there is a point where the LEDs would both be sat on this bit, but instead they add together and add up there. So you can add the carry in there. So we've got quite an interesting little sequence going on, and I think the add is correct. So we need to get the numbers out of there. So let's think about that. Right, so obvious way to pull the numbers out, because we basically, whatever we have here, we want to be able to optionally put it onto the bus. So let's go with one of these 74LS541 line driver chips. Now that's tricky because power is going to line up annoyingly for us here. Here we've got these 2 active low. enable lines. So I want to bring that one high temporarily. Okay, so if we bring this line low, that means this will control the output of the line driver. And we need to connect the outputs here into the inputs up here. Now in hindsight, it would have been slightly better to have this one notch over to the left, have the power cables the other way around between these two, and then made these lines line up. But I'm not about to recut all of these yellow wires just to do that. Okay, I have made up a nice big DuPont cable for connecting this back to the main bus. I fear there is not going to be a super neat way of doing this. There is at least a functional way of doing it. And the control line here needs to come across to one of the read lines here. So I think this video is going to be long enough as it is. So in the next video, what I will be doing is connecting this up to the bus control, and then these control lines here we can connect into pipeline stage 1, and then we should be able to update the control logic in the pipelines and write a little bit of code that's actually going to add some numbers together. So that'll be pretty cool, actually. So we have some adding, if not actually completely wired into the processor yet. But thanks for watching. Goodbye.